Hi everyone, welcome to Intarea, to the very last session. This is Juan Carlos and Wasim, your chairs.
Hello everyone.
Thanks. Hi Wasim.
Hello. Welcome everyone.
So we're going to start by the usual. Please join the queue before participating to make it easier for everyone, and be kind to mute your mic unless you're speaking. Preferably turn off your video. If you're presenting, you want to turn on your video, that's fine. If you have questions or any doubts about how to operate media code, you have the links there on the screen. The note well, this is a regular IETF meeting, so please be aware of the rules. By participating, you agree to follow the process and policies. If you're aware of any patent that covers any contribution or something that has been said here, please disclose it. And then as a participant, you are acknowledging that this written audio and video records may be used and may be made public. We will for sure make sure that you respect other participants. And if you have any questions, you have all the links there to the different PCPs and procedures. As a reminder, we're going to be taking minutes. The meeting is recorded. Your presence is being logged, the usual blue sheets when you log into the data tracker. We're going to ask, please, to help us with the minutes by clicking on the code EMD in Miteco or on the link that is in the slides, so that we can keep track of what it's been said at the meeting. And again, bear in mind that recordings and minutes will be made public and subject to discovery in the event of litigation. So the agenda, we have quite a heavy agenda. We are going to start by giving you an update on the working group status. Then myself, I'm going to provide an update of the Medinas BOF that we had on Wednesday. Followed by that, Chatura will talk about the tactile internet. Then we have functional addressing from Torlos. Then problems and requirements of satellite constellation for internet, Lin Han. Challenging scenarios and problems in internet addressing from Yihao Jia. Followed by gap analysis in internet addressing from him as well. Requirements and scenarios for industry internet addressing, Kiran. And finally, transmission of IP packets over overlay multi-link network, the Omni interfaces by Fred. Is there any bashing or questions about the agenda? Eric?
One comment, we need to get a minute taker on this. Is there any volunteer, or did I miss somebody that already volunteered for doing it?
Can someone help us with the minutes? Of course, we're going to be also taking minutes, but can we have someone describing?
It can be done after by listening to the recording, of course, but it's way better if somebody not record everything, but only the questions and the answers. In the commit, it is the top icon with the square and the pen on it. Doesn't need to be accurate too much, right? Because everyone can fix it later. But we need to get one.
Do we have any volunteer? Please.
Indeed, please. Basically, I'm afraid that we cannot start without this. And if you've never done this, go on, Wasim.
Please, If someone can do that,
Mhm.
would be much appreciated.
So Luigi says that he can do it later based on the recording. Do you mean helping us with the notes? If so, it doesn't have to be all the time you, but it would be appreciated if you can help us with part of it. Luigi?
Yes, I just wanted to say I can help with minutes. I mean, I usually like to do it listening to the recordings. If that helps, I can do it.
Perfect.
Okay.
Thank you very much.
That would
That's
be great.
appreciated.
Thanks a lot, Luigi.
You're most welcome. Let's start.
Great. Thank you. So indeed, let's move on. Quick status update for the generic UDP encapsulation. This is draft IETF Intarea GUI 09 that was submitted to ISG, and it's been there for quite a while, close to a year. So I guess this, if there's no interest in advancing this document, it'll just die soon. I don't know, Eric, do you want to say something about it?
Yeah, I mean, it's the latest version is mostly 2 years ago. I submitted after my AD review comments on the mailing list about a year ago. In October, it will be 1 year. My plan is that, and the authors are not here either. So in October 2021, I will declare this document dead, meaning it doesn't progress. It's no more part of the working group. We can continue later, of course, right? But it will need to restart from the working group adoption. Thank you.
Great. Thank you for that clarification, Eric. Okay, so then I'm going to give you a quick update of the Madinas BOF. As a reminder, Madinas is MAC address randomization and the effect on network address services. It was a BOF held first at IETF 109 and then followed by a side meeting at IETF 110. So that was a non-working group forming BOF. And for this IETF 111, we had a BOF working group forming where we discussed more in detail the charter. In this case, the idea is for the group to work on the problem statement, the use cases, and the effects of MAC address randomization on different network services, with the idea that the group will only work on informational documents in the beginning, but also, and very importantly, will help with liaison with other SDOs and working groups on this topic. So to give an idea of the result of the group, there was very interesting support about the problem statement, that people were interested in the topic and willing to contribute. So right now we are finalizing the charter, drafting the charter. And if you are interested in the topic, I invite you to join the mailing list. You have the link there. But that's pretty much the update for Madinas. Eric?
Yeah, and just to be clear on the process, as many of us know, the working group is not yet formally created. I personally have good feeling about it after the BOF and the energy which is behind and the draft charter. It will be decided next week by the IAB and the IAC whether this working group may proceed by the chartering. But I'm quite confident it will be. So stay tuned on this one. And of course, collaborate on the charter revision at some point of time when we'll be discussing with the community.
Great. Okay, so thank you very much. With that, we are going to move to the next presentation. So we have Chatura, please, if you want to share your slides. It's your time.
Hello, can you hear me?
Yes.
Okay. Okay. So you prefer me to this to share the slides, I believe.
Yes. So I'm giving you access now.
Okay. So 1 second. Sorry. Sorry, for some reason it says no slides available.
Okay, do you want to share your screen then?
Let's see. Should be okay. Yes. One second. Sorry about this.
No,
Okay.
it says that screen sharing being started.
Okay. Please let me know when you can see the screen.
Yes, we can see it.
Right. Is this set up okay? I'm not actually. Is this okay? So.
Yep.
Right. Okay. Sorry about that, guys. I'm Chatra Sarakchandra, and I'm going to present a draft that we've recently submitted on requirements for tactile internet, which I have co-authored with Morteza, which I believe also online, and also Mona. This is sort of the table of content. I would not go too much into detail because this is the first time I'm presenting this, as also it's the first time presenting in IETF as well. So all of the content here is new. The main goal of this draft is to present tactile internet or TI use cases and then potential requirements that can be addressed within IETF or IETF groups. This is purely an informational draft that is meant to address discussions in this area. So, what is tactile internet? Tactile internet is a new ICT paradigm which can provide ultra low latency, ultra reliability, and real-time communications services to emerging applications such as teleoperation, immersive VR, and haptic communication, which involves closed-loop, human-in-the-loop interactions. These applications require multisensory, multimodal communication where information related to audio, video, as well as touch are communicated in real time. Although there are various existing related efforts in standards to address some of the requirements, for example, the work in 5G URLC in 3GPP, a more holistic approach could be taken to support all TI requirements for efficiently supporting TI applications. There is also a working group on tactile internet in IEEE 1918.1, which looks at aspects such as applications, architecture, and haptic encoding. TI applications often involves bidirectional communication, as can be seen in the figure, which shows a teleoperation system. In one side, you can see a human operator which controls a robot in remote task environment. This is done by providing control input by the human operator while receiving various feedback related to the environment in the remote task environment. There are various end devices or terminals or tactile devices such as sensors and actuators on either side of the both sides of the figure. So usually, you can imagine. So these sensors are often used for capturing those multimodal information, while actuators are used for executing the instructions, for example, provided by the human operator. The tactile internet networking infrastructure enables the transmission of information generated by those devices in both sides, and transmits them to bidirectionally. So let's look at some use cases. Remote operations, automation, smart factory are key industry use cases that are enabled by TI. For example, TI enables remote repairing and maintenance of machines. This could be in high-risk scenarios where it might be too dangerous for persons to go, or when it's too not possible for an expert to be physically present at the time. Often, such remote operation scenarios require multimodal, that is, for example, audio, video, haptic feedback for performing complex tasks remotely. Healthcare is also quite an attractive use case for TI, which includes telesurgery, telediagnosis, telerehabilitation, telementoring. For example, telesurgery allows specialist surgeons to perform operations remotely. Even surgical robots that are being used today, although the operators are operated locally, performs highly precise operations while minimizing the invasiveness of the operation being performed. Tactile communication is very important here also, as tactile feedback is crucial when performing highly precise operations, as also mentioned in the previous use case. Based on an article published in, I believe, 2019, a surgeon has performed a remote operation using 5G technology on an animal from 30 miles away, and this is considered a world first as well. Entertainment, one might argue that is an obvious scenario where haptic feedback and communication can be incorporated, for example, by providing haptic feedback for VR gaming, we have tourism, VR art applications, or even existing applications for elevating the user experience of these applications. However, in collaborative VR applications, added haptic feedback will improve the user experience to that of or close to the real physical interactions. Haptic-enabled TI applications can improve experiences of both learners and teachers in training scenarios, training applications, and not only enables users to train remotely. Audio, again here as well, audio, video, or audio-visual tactile enabled learning experiences provide learning environments that are closer to face-to-face environments. And collaborative learning, learning applications can also be benefited, such as military applications or sports applications, where it requires learners to solve problems in a collaborative manner, where multisensory interactions are key. Now, we're going to look at some of the requirements. So There has not been a media type for haptics until recent adoption of haptics as a media type in MPEG systems file format subgroup in ISO BMFF. So like audio, video, haptics also are related to a separate sensory system and can benefit or even better suited to have a separate media type. Adopting haptics as a top-level media type in IETF is an important step towards further development of haptic communication. In fact, there is a specific draft discussing this specific fact in dispatch working groups, is referenced here. So ultra-low latency is quite an important requirement for tactile internet applications, because real-time haptic interactions demand for 1 millisecond ultra-low latency, as can be seen on the example provided in the figure. And we extracted this figure from a ITU technical report on tactile internet. Timely delivery of messages is crucial for tactile internet applications such as remote maintenance in industry and telesurgery in healthcare. Like low latency, ultra-high reliability is a crucial requirement for tactile internet applications as well. As you can imagine, hindering the reliability of communication, for example, in open heart surgery, telesurgery, applications can have very undesirable consequences. All multimodal systems belonging to the same application, all multimodal streams belong to the same application must be played back to the user in a synchronous manner. Otherwise, this can lead to reduced quality of experience and issues such as cyber sickness. Multimodal, for example, audio, video, haptic streams of the same application may be distributed even among multiple tactile or terminal devices. For example, these days users own more than one device, often are surrounded by multiple devices, and these applications may as well use those devices for providing experiences. And in such scenarios, those streams may be distributed among those devices. Due to various network conditions and lack of support or assistance for synchronizations, these streams may arrive at corresponding devices out of synchronization and leave the applications to deal with it, and can also lead to delayed playback or interruptions even. Therefore, it is important to provide further support or assistance for synchronization for both single and multi-destination scenarios, or single or multi-user, multi-device scenarios. For satisfying stringent requirements of tactile internet applications such as ultra-low latency, treating networks as a black box might not be sufficient. Adapting application behavior using coarse-grained measurements of the network resources may not also be enough. But maybe a more collaborative approach could, where applications and networks can better express their requirements and constraints may be required. In such scenarios, networks may manage their resources to satisfy application requirements, and applications may adapt themselves to network constraints, of course, when possible, at least better than today. It is also important to have mechanisms for coordinating communication. Such coordination mechanisms may allow various networks and network conditions to be intelligently handled. For example, there might be scenarios where data packet scheduling across multiple terminals or access networks are required, especially in scenarios such as multi-device scenarios, where you might have multiple devices and those devices connected through different access networks. Instability of underlying network conditions of one stream, therefore, may affect the whole multimodal user experience. TI, tactile internet applications can be highly dynamic. For example, in multi-user scenarios, especially when user profiles, user dynamic relations, and interactions are present, and multimodal information corresponding to each individual user, especially related to the user perception, can be distinct. For example, a VR environment where multi-users act on the same environment. Perceptions like individual viewpoint, the operations performed, tasks being performed, type of tools may be used, type of objects that these users interact with. The information corresponding to each individual user may differ, and throughout the whole execution of the application as well. And therefore, multimodal data that's been transferred using separate streams to users may be personalized accordingly. If you had a chance to read the draft, you might have noticed made a couple of changes. Well, one change, we've changed the term from service requirements to application requirements to sort of better reflect what we present in the here, and to avoid ambiguity and confusions as well. And that's pretty much it for this presentation. And questions, comments, suggestions are very welcome. And also, if there are any suggestions or other suitable group that might be interested in the draft, they're highly welcome as well. We've had this discussion also on mailing list. We received a number of suggestions, and thank you for those as well. And we will take them into consideration. Thank you.
Thanks very much. So we have people in the queue. So Colin.
Okay. So I sort of put my question out back when I saw the latency requirement about 1 millisecond. And I mean, I was wondering if you could speak a little bit more to why it's that low when humans are in the loop, because I think there's been a few other people too that seemed probably faster than was needed for anything that involved human interaction, which presumably, since this is tactile, we're all talking about a human being in the loop at some point. And I get the point for the synchronization and the low latency. I'm just trying to push on how low a latency do we need on one side of the question. And then on the other side of the question, I mean, if we do need those types of latency, is internet technology really appropriate for that? Like, even if we're running in a LAN, I don't think that we can reliably deliver 1 millisecond. So I'm sort of curious what your thoughts are in both do we really need that low, and is this technology that we're talking about at IETF even remotely appropriate for that? Thanks.
Thank you, Colin. With regards to the 1 millisecond requirement, my understanding is that it depends on the type of application. For example, that's why it's specifically worded as interactions, maybe, where it is it has to be sort of an online interaction. If you are, I guess, just transferring that over, just the network over, it's less of if it's a less of interaction, I guess, then it will be, it won't be that much of a requirement. But it is a known, sort of well understood sort of a requirement at this moment in time. To answer your second question, this is exactly why kind of we wanted to bring it up, to sort of ask the question whether how or whether and if can the internet sort of deliver on this promise or on these requirements. At this moment in time, I don't think all the sort of even not even less of solution, but even these problems are clear. But there's some of the requirements we try to sort of list. But yeah, so this is still up for discussion. Thank you.
Thanks.
Thank you very much. Stuart?
Hello. My question about this presentation is, it's not a surprise to anybody at the IETF that we would like a network that is high throughput and low latency and reliable. I don't think anybody would fall off their chair and think that was an amazing insight they'd never heard of before. In fact, I would say for 40 years since the internet was created, the goal has always been to make it a reliable, high throughput, low latency network to the best of our ability with the technology we know. So the fact that we want this is not a surprise. Is there any proposal for how to do this? Is this talking about FQCODL, Pi, L4S, something else? What is the proposal for how we would get from where we are today to something better?
Thanks, Stuart. Yeah, you're right. I mean, yes. So always we try to, we've try to reduce the latencies and provide higher bandwidth and etc. Exactly as to a proposal as to how to sort of solve this, I do not particularly have fully solved the whole problem to meet all requirements. I do not have an exact answer, but I believe maybe addressing some of the requirements in different areas, such as URLLC and various other areas. I think eventually that's where we are moving towards ultimately. I think also on top of these low latency and high reliability requirements, there's also this added modality of communication there as well, which is haptic communication. I guess the question for the network community is that do we need to handle those traffic differently to the other ones as well? As I mentioned, there's already a discussion on having haptics as a top-level media type as well. So that's sort of other aspects that brings these applications into the sort of picture.
Okay, so my suggestion, if you want to move this work forwards, is propose ways to solve these problems, because I think the existence of the problems themselves is already known. The question is what to do about it.
Okay.
Sure. Thank you, Stuart.
Thanks, Torles.
Yeah. So going back to Fluffy's maybe rhetorical question, would we even want to have these type of stringent services? I think that there is no reason why IP networking couldn't be as good in any of these quality parameters as any other packet networking technology. And yet, if we look at the past 20 years, then I think it would be fair to say that for anything that provides better than best effort, IEEE, with efforts ending up in TSN, have really eaten our lunch, and we're struggling for a comeback with TSN. And maybe there is a more generic question of how the community could be more inviting to application use cases, industries that are having more stringent requirements like this one upcoming.
All right, thank you very much. So if there are no further questions, then I guess we can move to the next presentation, which is Carlos?
Thank you.
If you can accept my request for sharing slides. There is
Yeah, let me revoke this one and grant you.
Okay, what do I want to talk about? Ah, this looks good. Okay, terrible name. You know, we'll pay pizza and so for better name. No, slide not moving. What happens?
Yeah.
Right. So there have been, you know, recently proposals in Intarea and also, you know, outside of Intarea in more with research focus about what we can do with addresses, different semantics and so on. So I started to think about one type of problem space that I think we haven't well explored, which is in the title, independent address spaces. And I've presented on IoT Ops, so the problem statement might be something to take out of this work and work in maybe an operational group. And there obviously the solution proposed solves other problem, I think, that are much more shorter term and much more obvious to people in a better shape than the existing solutions. But I wanted to focus really on what might be the most offensive option that is in here, given how we've kind of said this is not a good thing to do. So let's say the generic issue that I see is that in our network layer protocol IPv6, we've pretty much focused on the one core problem we needed to solve in the 90s, which is the internet, and forgetting a little bit that we need to have a network layer that doesn't only serve these 10% of the IETF deployment iceberg, which is 90% under the waterline since 8799. We're calling this limited domains, and it includes everything from embedded IoT devices over to a lot of other IoT and OT, energy sector, manufacturing, oil and gas, transportation, nationwide networks, and obviously not to the last service provider networks with MPLS, which all have nothing to do with the internet. And if you look then at what support do we have in IPv6 addressing for these, it's just a terrible, you know, set of limitations and challenges. I wrote some of them on the left-hand side. Read the document for more, and certainly a lot more to go on that. So the independent address space is something that you see very often in these type of IoT environments with larger networks, starting with, you know, simple hierarchically built environments, like you build a simple machinery out of an Ethernet with attached sensors, actors, controllers, and then you plug them together for a larger machinery with another level of networking, and then yet another one, and ultimately these things become assembly lines. And then you look at an overall, you know, smart manufacturing network of networks, and you can see that there's a lot of plugging together hierarchically in any other shape or form of networking, differently complex networks, where really the last thing you want to have is having to bother about a single global address space into which you would, according to the end-to-end internet principle of IPv6, have to address everything in these networks into. So, and the one typical example from IPv4, which also is why a lot of these things are still happily built with IPv4 and RFC 1918 address space, is exactly such a machinery. 1000X are the fixed addresses assigned to every instance of the product that is being built. In deployment, the gateway, which is an Ethernet switch. If you ever wondered why industrial Ethernet switches have crazy NAT, this is it, right? You're basically mapping, let's say, with the standard mechanism, the third byte of the address to the orange Ethernet, so that multiple of these type of machineries can be disambiguated in their address, and then to the green one, another layer with the second byte of the address. Maybe you even go into IPv6 for larger scale, but obviously this is not part of the standard architecture of IP. It's an afterthought that people got out of RFC 1918, and IPv6 with ULA is actually worse and doesn't even offer any more bits of, you know, address that you can munch with. It's the same 16-bit that you have free as an IPv4. So with that being said, let's take a look at a simple example scenario explaining how variable length addresses with the semantic, I think, is easy to implement, would be able to solve that. All our addresses are written as simple hexadecimal addresses separated by optional dots, just to show, you know, where the address is segmented, has no other functional. Everything is modulo 4, so that every structural, so it prefixes, for example, just modulo 4, addresses length modulo 4, so we don't cut into a single digit. Now, the important part of the address allocation within a particular network is that every node gets assigned a prefix that is not overlapping with any other node's prefix. And then you just use normal IGP routing. These are all, let's say, like loopback addresses routed so that they're fixed, permanently assigned in a network. We've got a lot of experience in that with service providers, so very easy to do. So now what do we start? So somebody builds a network from a template like an industry standard, like I've seen it, and then even using addresses that people were recommending, which is fine, very simple. These are all just 8-bit long addresses, so very short. And then somebody else comes along and builds a second network, exactly the same thing. Maybe these two are machineries. Of course, topology might be different. Addresses, in this case, even totally overlapping, but whatever the overlap is. So how do you now interconnect them? And this is basically where the proposal comes in. What you're doing is one network is interested to connect to the other. In this case, it's the blue network on the left, wanting to connect to the network on the right. So it basically asks for 2 links into the network. And obviously from the right network, it's being given 2 address prefixes, 1 for each of the links. They're getting configured. And so we basically have in the blue network now 2 edge routers between 2 independent address spaces that are overlapping. So how are we sending packets? And this is the core of the forwarding. So as you can see in the first line here, 52 on the left-hand side wants to send a packet to 35 on the right-hand side. The address it's sending to is 22135. What that means is within the blue network, the packet is forwarded purely on the destination address prefix 2. Once it arrives at 2, the next 2 digits have the first one 2 saying, well, this is a function of the rest of the address is telling you which link you're going to send it. So let's say link 1 is exactly the link from RA into network 2. So what then happens is RA, the only thing it needs to do is actually this 12-bit lookup 221. It strips that prefix. It takes address 35, recirculates that into the forwarding table for network 2. Opposite can happen optionally if desired for the source address. You prepend the prefix to return through RA before you forward the packet into network 2, so you have symmetrical traffic forwarding back. And obviously this scheme can be expanded to arbitrary topologies of networks with independent address spaces. So very simple forwarding, except for the standard prefix lookup that we're already doing. We have a strip address and prepend address function that we would need at edge routers between two networks with independent address spaces. Now, if we generalize this to show how this type of very simple semantic approach for building functional addresses, let's say an address is a sequence of functions. Functions could either be, a new other semantic, or it could be, as shown here, a node prefix, and then it's followed by a function code and parameters. Function code, we had function code 2, which is this, inter-network routing, but it's easy to come up with other function codes. Use the control plane like we've learned in MPLS to assign semantics. So let's say function code 0 could just be followed by a parameter that is the transport protocol, and function code 0 means, well, punt it up to transport stack, and here is your transport protocol. So we'll eliminate another currently special next protocol field in the packet header. Or we're just doing the packet steering that we're doing with SRMPLS or SRv6, right? So pretty much the same thing. You're removing the prefix, but you're not doing anything more, very much the same as we would do with function 2. And then all this SRv6 programming obviously would also very easy to add into the address as new functions with parameters. And it wouldn't be a fixed 64-bit like we've got in SRv6 now, but it could be, no wasted bits if you don't need it, and it could be more than 64-bit if there is a lot of instruction for a particular hop. And then other semantic, obviously, being something to use for multicast, beer, CCN, whatever you have. So there is a lot that could be said about naming and address resolution. So how do you know where you go to? What's the name of it in the first place? The addresses are, to a good extent, names already. And a lot of network deployments like industrial and others where you don't need another namespace like DNS. But if you want to do it, we have a lot of experience with that as well. There is a very interesting 21-year-old enterprise net multi-homing solution from Yakov that I have in the references. So all these naming and addressing things, I think we know how to solve. Maybe last, just to see how simple this can become in the forwarding plane. Let's say we actually do ever want to go beyond IPv6 in a backward compatible fashion. We could build a header that is simplified, removing all the stuff we don't need in most of the cases, just got variable length source destination addresses with their length indication. We still need hop limit, ECN, new version, obviously, so that it's not changing the v6 header as it is, but then all the QS stuff, for example, could go into an extension header. So simplification with more flexible functionality. Many add-on functions we have an extension header could simply go in the address. Right, so here is the boring summary. Here is the hopefully more entertaining summary for the end of the presentation. And I think we really, have gone through an evolution of domesticating addressing, and I think we should be ready to take the next step, right? So this all started with NET and IPv4. Then we went through a lot of experience with 26 IPv4 to v6 transition solutions, most of which we would probably not like and feel it's wild beasts. But some of them actually are better. We have good, functional structure use in v6, especially with multicast. We learned a lot and know how to do better with the address processing in MPLS and source routing in SR, MPLS, and SRH. So, I think with a proposal like this, we would make exactly all these things that we've done in the past 10 years, especially in very, ad hoc fashions based on a 20-year-old or 50-year-old long address IPv6 protocol a lot better if we would allow us to think experimenting with a new base header. And I think that's it. Thank you very much.
Great, thank you very much. Are there any questions? Luigi.
Hi, just a quick clarification question. So in your schema of the addresses, you have a way to encode the function of something. At some point, you made an example where code 2 identifies a link, which means that now you have an identifier or an address or something that allows you to identify a link. And in the example that you gave is about Intarea. So do both ends need to agree on the same link identifier, and does that explode somehow the size of the address?
No, effectively, this is just a path identifier, right? So you're basically saying, go to this edge router. That edge router removes its own prefix, then looks at what comes afterward, which he has locally defined to be, let's say, the digit 2 means the next digit is, 1 out of 16 links into different networks I could go to. And that's just all part of what could be done in the control plane. It doesn't have to be hard-coded in any, forwarding plane spec.
Okay, thanks.
Thank you. We have Eric in the queue.
Yeah, thank you, Torres. Challenging discussion and interesting. Do you see this applicable to the complete internet or just inside a small domain like an industry?
I never know what quote the internet is. To me, the internet is a best effort only overlay service on top of thousands of underlay networks, right? Service providers, enterprises, what have you. And I think obviously everything needs to start small in underlays, and we haven't gotten anything new into, quote, the internet, not since 1995 when it commercialized, right? We didn't get DiffServ into it. We didn't get multicast into it, right? We've been struggling for 15 years with ECN. So no, I don't see that the internet service as we've defined it now is something we're going to get anything new into. But we do have DiffServ, we do have multicast in a lot of metropolitan size service provider networks where they're offering it to customers, right? So is that the internet? Right.
And basically, and without any yet, I should have specified it before. So it's basically a single domain based on your description.
No, I think this part, especially if you think about what is a single domain, right? So if I build a manufacturing floor, the responsibility for the components inside of it will lie with the vendor of that equipment, right? It's maybe plugged together by a fabric owner, but the fabric owner or the manufacturing plant owner plugs together equipment that, which hierarchically has ownership from people who are selling it as a service and so on. So, but it's not your internet interdomain between service provider with BGP. That, I think, is the last place to start changing something.
Okay, thank you. Interesting anyway.
Mm-hmm.
Jan?
Hi. Very interesting. However, question, following up actually on Eric's question. So I am quite surprised to see the variable length header on your slide after all these discussions we have in every IETF about, oh my God, IPv6 extension headers are so hard because they're variable lengths and we don't know how to process them. So what do you think about that conflict?
Yeah, exactly. So I was trying to strip down the complexity in the forwarding plane because, going through a chain of extension headers, and I said through 6-men, which was very enlightening, right? I don't want to have this. So I'm trying to figure out how we can make it as simple as possible. And I think we could learn a lot from MPLS. I think this proposal does that because if you look at it, you see exactly the forwarding steps, right? The forwarding step was just longest match prefix lookup, then one rewrite, then recirculation again for this function, right? If you take the other function, which is steering through the network, it would be equally or cheaper than, let's say, SRH header processing, right? Equal to, I think, MPLS forwarding. Okay, we need prefix lookup instead of fixed 20-bit address lookups, right? But yeah, I think, bring it on, right? Let's have the battle of comparison of the actual forwarding plane processing complexity. That's, I think, a good topic. And, we did 2 years ago, we were talking about that as well in terms of let's understand more what forwarding planes can do these days. In the MPLS design team, there are a lot of people standing up telling us we can do more now. Let's explore that.
Cool, thank you.
Mm-hmm.
Great. Thank you very much. Are there any other questions? All right, so thanks again. So we are now moving to Lynn.
Hi. Should I share my screen or?
Yeah, you can click on preloaded slides or share screen as you prefer.
Okay.
We are granting you access now. Yeah, we can see your screen.
Can you see it?
You can go ahead.
Can you see it?
Yes.
Okay. So my presentation is about problems and the requirements of satellite constellation for internet. And this is only informational draft, since there's no dedicated research group or working group for satellite. And so we bring this to internet area. for presentation. First, background and motivation. So everyone knows that satellite network is becoming as a hot topic, even for 5G or 6G. And Starlink has provided a beta service, which proves that it has some competitive quality over traditional ISP. And now the Starlink has launched about 1,500 satellites and over 10,000 subscribers. And Elon Musk predicted we'll reach 500,000 and quickly. But the deployment of the service of satellite Starlink satellite networking is pretty preliminary. This is information from the Reddit because there are a lot of technical discussing in that group. So we can predict what is the kind of technology the Starlink is using. And also this can be predicted from the service Starlink has provided. It only can provide service in very limited area. And also the quality is not good. It needs a non-provisioning. Besides Starlink, more countries and more companies plan to launch LU and VLU. So we will see that what is the kind of problem in current Starlink, current satellite motivation, satellite network. So motivations. So this draft just analyze the issues and try to draw attention from the community, and probably will drive better solution in the future. Right now, the analysis will just give the estimation from the orbit coverage and the communication time from for the ground station to satellite and between satellites. Then analyze the feasible operation model for satellite constellation. Finally, we will list the problems we think it should be resolved. And as the IETF draft, we only focus on the layer 2 and above. For example, mobility, routing, and switching technology. We don't touch the radio or spectrum or those kind of physical layer issues. First, the satellite orbit elements and position. This is general knowledge of astronomy. And they have many parameters, but fortunately for the LU and the VLEO, the orbit is very close to circular. So we only use the two parameters. One is the inclination, another is the longitude of the ascending nodes, which will describe what is the angle of this orbit turn in this direction. Also, third one is the altitude, of course, because it's a circular orbit. We don't use this, which is related to the eclipse orbit, and also this. So the real-time position of the satellite is described by this true anomaly. Basically, from the altitude and the inclination, we can accurately predict the satellite's 3D position. So this is kind of a real orbit. The red one is we call the polar orbit, which has inclination 90 degrees. Unfortunately, this orbit is not used because we can see that it has the highest coverage at the polar area, which is doesn't have population. So in the real deployment, they always have inclined the orbit plane. The green one and this blue one. This is some basic math about the satellite orbit, and from orbit we can estimate the coverage. This is coverage, and also we can estimate the speed. So basically, the only known parameter right now for the orbit is altitude. And from the Starlink practice, they give this called the beta angle, which is elevation angle. Means that this is when the angle less than this, the satellite is invisible and the communication is not possible. So from this, we can calculate this anchor length. Then from this similar as cellular communication, we can easily calculate how many satellites needed to cover the whole Earth. And also, we can estimate the maximum communication time for any ground station. For example, if a satellite is moving from here to here, then the whole, from here to here, the means that the diameter is the longest path the satellite can move for one ground station. That distance can be used as an estimation for how long time the communication can be lost. So this is some data we have calculated. This is the altitude of satellites, VLU, LU, and different altitude. For LU, normally the altitude will be below 1,500 kilometers. And the VLU will be below 500 kilometers. From the practice of Starlink, it seems like right now the current technology still cannot working very well for LU, means that the distance or altitude too high. Right now, the Starlink has moved a lot of satellites before plan to launch at LU to VLU. So this is alpha angle we calculated, and from that we can calculate the radio of the coverage. We can see the radio of coverage is from a couple of hundred kilometers to over 1,000 kilometers. And this is the minimum number required to cover the whole Earth. But this estimation is using inclination angle 90 degrees. If the angle is less than that, the estimation will be similar, but it's not important because right now the real deployment will have much more density than this requirement. So here we can estimate the communication time, maximum communication time. And this is for the different altitude of satellites. We can see maximum communication time. For VLU, for example, this is only 300 kilometers, only about 100 seconds. Even for LU, only about 400 seconds, which is less than 5 minutes. Remember, this is maximum communication time. So normally the communication time will be less than this. Here we also estimate for the inter-satellite communication, how long time the communication can last. So for example, we have a different intersection angle. If the zero means that the satellite moving with the same direction for different altitude of the satellite. And we can see even with the same angle, if with the same direction, if the speed are different, in the draft we have more data here. This table is not complete. We can see how long time the communication can last. For example, this one will be less than probably 20 hours. So for inter-satellite communication. Next, we'll talk about the satellite networking. This is not about the issue of individual satellites. This is about satellite constellation. So the issue will be much more complicated. And first, we can figure out what is the possible operation model. Right now, we can easily think about two models. One is called a satellite relay. Satellite relay means that the signal will be bounced between satellite and the ground station, either by one satellite or by multiple satellites. The second one will be signal will go through the inter-satellite link between satellites. But this technology is still not mature, and Starlink has started to experiment some, but definitely is not used. Right now, as we can predict, only this logic is used. So even this multi-satellite ground station really is not used because that's not a simple issue. I will show that. And from the estimation, we can see the satellite to ground station communication is very dynamic. The maximum time of communication can only last probably less than 5 minutes. And if we bring in the inter-satellite communication into the picture, then the communication between satellites will be also not very steady, not like a current service provider network. It will keep changing every day, for example. So from this, we can see that satellite constellation network will be very dynamic in terms of topology, and also it will lead to the very frequent handover. So common issues, first is mobility. For example, right now we have already have many mobility technologies there, but the current mobility technology may not be helpful for this spatial scenario. For example, right now all mobility technology is based on the assumption that mobile and communication node plus the static base station and provider network. So for example, the 3GPP wireless, the cell phone is moving, base station is not moving, mobile call is not moving, service provider network also not moving. So we have an inter or intra handover there. The scheme is relatively easy because the mobility is very limited in very limited devices. And also IETF introduced mobile IP, mobile V6, proxy mobile IPv6, and Lisp. And in recent presentation, I saw the ATN also come to picture, but it's still based on all these existing technologies, even it is used for the airplane. And the satellite mobility is different. We will have and communication node static. For example, if you use the satellite for home access, your ground station is static, but the provider network is moving. Right now, if you're using the satellite as a provider network, it will be keep moving. And also the moving speed is fast, as I showed that the communication time is very short. Second things we have to consider is that in satellite, the power supply is very constrained. Because of this, then packet loss forwarding should consider this limitation. Also, the link speed is limited. For example, from the current research, even we use laser for inter-satellite link, probably the link speed is still below the 10 gig from the current technology. Here, I will show some issues for the different operation model. And I don't list all the big requirements and the problems, because some other problem I think we have solution. And it is listed in the draft, because draft has over 30 pages. I don't want to list some less important issue here. I just want to show what is the critical one. For example, if we only use one satellite to do the communication, it will be the same situation as we use the GSO currently, for example, geosynchronous orbit satellites. It's just physically reflecting the signal between ground station and the satellite. It will be easier. But if we have multiple satellite really come to picture, it is not that simple. Why? Because the real satellite constellation will have a lot of ground stations. So, for example, from Starlink request from FCC, right? They request over 1 million ground stations. 1 million ground stations in which they have 3 types. One is the end for end user. Second is that the ground station can connect to internet. Third one is the ground station is called gateway ground station. These two called gateway ground station, but some gateway ground station is not connect to internet. And from current data, in the United States, there are already about more than 100 ground stations there. So with so many ground stations and the number of satellites, the things will become complicated. For example, even between two ground stations, right? They may have multiple satellites come above, and all satellites can provide a service. Then which one you will choose? It's not a simple issue. Second is that what is the ground station you will choose to reflect your signal? For example, you have multiple satellites, you have multiple ground station, and which one you will be peer for your whole path. For example, this is a final, we can reflect a signal between multiple ground station and satellite to reach one ground station which is connected to internet. Then which path will choose? You may have a different paths. So this is just three typical issues involved in the multiple satellite relay. And of course, for all this, we have to think about how to solve it in terms of the protocol or technology.
Lynn, if you don't mind speeding up, you're running a bit late.
Okay, so next is about inter-satellite communication used for satellite networking. This is most complicated. And it will be combination of SL link and satellite ground station link. Ground station could be isolated or interconnected. Right now, the technology is not mature. And two key issues. One is the inter-satellite communication. This is not the direct concern. We only concerned about the routing and the switch. Here is the issues. All satellite constellation is moving. And according to traditional technology, we should use IGP, for example, eBGP between the internet and the ground station. Then also eBGP between the local internet and this. Then if there are so many ground stations and so many network, and if the topologies keep moving, definitely the current technology cannot handle it. For example, we will have massive IGP flooding, and the BGP convergence will become a serious issue there. Yeah, that's my presentation. Just want to have more comments and feedback.
Thank you very much. So let me jump here in the queue. I'm curious about whether you are proposing to solve this at layer 3, because the problem has existed for a while, since the late 90s, when the teledesic network was first planned. They were already solving it at layer 2 with inter-satellite links. And then the internet was running on top of that. So is your proposal?
As I said, right now the historic work is only focusing in either physical layer or just using the individual or very few satellites to do the communication. But right now, if the satellite number become big and the ground station number become big, the issue will be different. No networking issue was involved before. Right now, the definitely networking issues involved. For example, the Starlink has think about it, provide a service in the ocean. When in the ocean, then there's no ground station can connect to internet. They have to use multiple ground stations. Then how to do it from the networking manner is a challenge. We don't have solution right now. We just want to draw attention for this typical issue. We just have some thought, but it's very preliminary, and I think they may have a different technology involved. Then maybe more solution will come to the community.
All right. Well, thanks. Then we'll continue on the list. Well, we have Eric on the line, and then we can move on to Dirk. Eric.
Yeah, I just was going to repeat a comment I made in the chat. I think that because the satellites are their motion is highly predictable, you don't need a routing protocol to deal with a bunch of dynamic updates, except in the case of inter-satellite link failures. If you have an SDN that can just basically issue routing updates to be enacted at various times in the future.
All right. So let's see if SDN can handle, because right now the time is predictable, but due to weather, due to the blocking objects, due to multiple satellites, the work is not that simple.
Okay, thank you very much for that. So we have to move on to the next presenter, Dirk.
Yes, thanks. Yeah, I'm going to present the next two drafts. I know they are listed as two separate items, but we combined them because the work is kind of like building onto each other. So this is about the internet addressing problem statement and the gap analysis. We presented the problem statement initially in the last IETF, and as presented there, the plan to continue with the gap analysis, which we have done since. So I'm going to provide an update on the problem statement and then go into the gap analysis. Yeah, it is. So I mean, Toll has provided quite a bit of the background where we're also building on. Internet addressing is the core method that allows me to direct packets in the global internet. But as similar to Toll's observation, we can say that a lot of the overall communication system actually, lies in limited domains, as described in RFC 8799, and those limited domains define requirements, node behaviors, address semantics, packet forwarding that may be significantly different from the internet addressing paradigm, while still potentially interconnecting or connecting to the internet or interconnecting over the internet. That very often requires that there are additional adaptation technologies involved that realize the distinguishing requirements of these scenarios. So that's the background and the observation from which we started the work in the problem statement draft. So the objective of both drafts is really, revolving around the question of whether limited domains should purely rely on IP addresses and therefore deal with the complexity to translate any semantic mismatch that arises from addressing the domain-specific requirements themselves, or should there be some flexibility for supporting those limited domains? And should there be a key focus for an evolved internet addressing? That's the kind of key question that we ask in the problem statement draft. For that, we formulated the problem statement draft by providing examples for communication scenarios where the existing internet addressing structure may be a potential hindrance, and then provide a first gap analysis. So we've done this already in the last IETF and updated this since, and we then provided a first gap analysis in which we provide an overview over the many recognized extensions to the core internet addressing properties as we can find them. So generally, our intention for these two drafts is to stimulate discussion on the emerging needs for addressing, really to get to a point where we would want to fundamentally rethink the addressing in the internet beyond what IPv6 and the current objective give us at the moment. We do recognize there are a number of proposals that fix aspects or claim to fix aspects. The drafts are not about promoting one over the other. This is really about the need to identify, to recognize the need, work towards an architectural approach, and think about extensibility and evolution of internet addressing to start with. So what are the updates on the problem statement draft? As I mentioned, we provided a first draft in the last IETF. We since then added 2 new co-authors to the problem statement draft. We provided input into a number of communication scenarios. Yamala from Rochester Institute and Paolo from Airbus. We simplified the structure of the problem statement draft in the light of the gap analysis. We moved a lot of in particular, section 3 was significantly updated. First, we updated the scenarios based on the input that were provided by our new co-authors, as I mentioned before. And then the issues were simplified in the light of the separate gap analysis. So the section is actually significantly shorter now as it used to be before, and some of the things were then moved into the gap analysis draft. Even though we added fragility and extensibility as additional concerns that were previously not listed as issues in addressing them. And then again, finishing with the actual problem statement. So these are the updates on that draft. For the gap analysis draft, so the main flow of the document, if you had a chance to read the document, which I hope you did, is to focus on 3 key properties for internet addressing. The first thing is the fixed address length, 232, 128 bits, the ambiguous address semantic with explicit locator and implicit identifier, and the limited address semantic support with mainly prefix-based semantics as they are supported. We then outline extensions to those key properties. That's where we place essentially the research work we've done to survey the number of, and I come to this in a separate slide, number of extensions that have been defined, and we position them as attempts to fill identified gaps in properties through these point solutions as we identified them to overcome those identified gaps. So the logic is that these extensions have been developed to address something that those who develop the extensions have perceived as a gap in internet addressing. We then identify issues with those extensions, which may be solved with an involved addressing or not. That's of course part of the discussion, and list those issues separately. And this you can find, the first part you can find in section 2 of the draft. The second part, the extension in section 3, and the issues in section 5. Section 4 is an overview table, which you can see here. So in overall, we identified 20 plus extensions that we described and referenced, and we're very happy to receive pointers to more approaches. So this is obviously a first run. This is a first version of the gap analysis. So you may appreciate that we have overlooked a number of extensions, obviously, but we've taken that initial list already as an evidence of shortcomings to internet addressing properties, you know, in the way of these extensions having you know, having addressed particular aspects that the developers or authors. We also included some research work and as well as existing standards. So there's a mix, a healthy mix of aspects on extensions that are described in that section, and we took this as evidence that those that develop those extensions have seen shortcomings of the internet addressing as a reason for developing them. So that's we as a summary of the issues we identified in red here, and the table is also in the draft, are issues that lead to limiting the address semantics because of certain ways with which the extensions were fitted into, for instance, IPv6, and needed to deal with the limitations that were given through that. Issues around complexity and efficiency, issues around security and fragility. Complexity and efficiency includes aspects like repetitive encapsulation, compounding issues with header compression, introducing path stretch, or making traffic engineering more complicated. And then we assigned, as you can see in the table, obviously in more words, this is just the summary table, what the various issues are and which of the approaches experienced or those particular issues. So these identified extensions provide an evidence that there are gaps remaining, if you will, because the issues, or some of the issues, either still existed or other issues were simply introduced through the solution. So what are the insights that we have so far from the problem statement and the gap analysis? Well, first, in the gap analysis, we identified many scenarios in which existing internet addressing shows shortcomings in realizing them. And that you can find in the problem statement, section 2. We also have identified that the internet community has recognized that shortcomings do exist to the original properties, and thus developed point extensions where they attempt to fix them. Right. So we are not the only one that recognize shortcomings. The internet community overall has recognized that. It's been working around those shortcomings for a very, very long time. We also identified that there are a number of compounding issues with those extensions that particularly increase the fragility when you consider point extensions and coexistence. We have a separate subsection in the gap analysis draft that addresses that particular aspect. And while we may see the idea of doing point extension to addressing here, and if I have an issue, I just do my own extension over possibly any existing or even a new header field as the powerful tool for extending the internet itself. What we have described in the draft is that by doing so, you start creating a whole tail of further issues that may just roll off that point extension, and it most importantly, it may increase the complexity as well as the fragility of the overall system. So yes, it may be a very, very powerful tool, but it's not one that comes without problems on its own. So what's the expectation that we have for our work going forward? Well, as I mentioned before, we want to promote the discussion to develop an architectural, but more importantly, a sustainable approach to make internet addressing extensible so that we can capture the many new use cases that we may identify. And looking back at the very first presentation from Shatura, question that could be asked in his particular area that he presented, whether or not there would be any addressing issues that one may identify for these particular type of new use cases he had in mind. I think I asked a similar question on the mailing list when he sent the draft around. We also believe that any inaction on our side will only compound the issues we identified. It doesn't make it better, they won't go away. And we feel that eventually it will hamper the future internet's readiness to address those and then support those new use cases. And not only the one that we mentioned, there are many others that also Torles pointed out in his presentation where the I spoke quite nicely. So what are the next steps that we have in mind? Well, for the broadened draft, we would like to expand on possibly missing communication scenarios, the same way we've done this after 1.10, to reach out to potential contributors to either extend or add communication scenarios that we may have missed. We're very interested in that, obviously. For the gap analysis, the extension we've identified are only the beginning, even though there are 20 plus add missing extension internet addressing, in order to elaborate on the issues through more evidence and references that we can find. Right, the more extension we find, the more we believe we find evidence that in particular they are compounding issues with developing those extensions. For that, we seek new co-authors and contributors, even would like to identify the right partners organization to work with, maybe even in the form of a liaison, like the one being proposed by ISO IEC, for instance, on underwater networks as an example that came to our attention, that one could use to maybe work with other organizations, in particular those that are bringing these new requirements into or towards the IETF. Goal ultimately for us is the adoption of the documents for future work in the Intarea, to go to extend the gap analysis, to move to a discussion on requirements and as to what the requirements for future solution may be before we start looking into potential approaches to solve these issues. The questions we have to the community is whether or not the extensions have shown that gaps to addressing have been identified. Is the logic we apply the right one? Are the identified issues worth thinking of different approaches, or are we just fine with doing those? Do we think we can avoid the issues, or just uncover others? Does the community believe that or agree that an architectural approach is required that make extensibility of addressing a key principle to future addressing? Or can we just continue doing what we've done so far with all the issues that we found in the gap analysis and may find in future extensions? And obviously, the question for us going forward, contributors to the discussion, want to work with us, push the discussion and the material further through extending the draft and working in future drafts. Thanks. That's it from my side. Questions and comments I would appreciate.
Thanks a lot, Derek. So are there any questions from the community? Okay, well, if we don't have any questions right now, I think that it's a topic that I invite you to bring to the list, especially if you're seeking to get some work in this area, in Intarea. We need to see some support, reviews, and so on from the group. So I encourage you to bring the discussion to the mailing list.
Yes, thanks. Absolutely, we'll do that.
Thank you very much. So moving on, we have Kieran. Okay, we can see it now. You want to turn on your mic? We can see the slides, but we cannot hear you. So I don't know if you hear me, but you need to click on the mic icon that is on the top left side of your screen.
I didn't realize I was on mute.
Okay, now we can hear you.
Yeah, so sorry about that. My name is Kiran, and this draft was first presented in IoT Ops Group on Monday. So what we are trying to do here is bring in the scenarios and some of the challenges which are related to industry control networks. Since in IETF, we have talked a lot about constrained devices or IoT in general, we haven't really focused on industry control networks and the lower level field bus type of devices. And with Industry 4.0 initiative, automation and smart manufacturing, bringing in IT technologies and OT technology, OT has become a lot more interesting topic of discussion. So since we discussed most of the stuff there, I just want to introduce this topic a little bit. And we'll just introduce a little bit of industry control networks, some of the scenarios and challenges we are looking at, and what are the possible functional areas that could possibly overlap between Intarea and IoT Ops work. So this is the general picture which even Torles talked about earlier, that industry control networks are built in a tiered fashion. You start from the device as a lower level, and then you keep stitching the different kinds of protocols together till you get to some system integration layer. And that's where from that point onwards, you will have some kind of manual or proprietary custom integration between your business logic applications that that collect the information from the industry control networks. But with automation, you need to have a much better integration between these two different types of networks, which up until now have just evolved independently. And if you look deeper into what are the different properties of devices in the process control, first of all, they are wired devices. They are not wireless devices, so they do not have specific requirements for saving on energy or how you can use them, or things which we have already discussed in the IoT 6LoWPAN and those type of technologies and protocols. But these are the critical factors are that they have direct process control loops. They process in the sense that you have to have time constrained networks. And since that work is already done in .NET, we were not really focused on that part. But the communication patterns, security, and the location, how the devices move on the factory floors, all these things are very well planned. So you have some sort of deterministic view of your network, that how it is going to behave. And because of that, operators of those networks, they very carefully engineer and design their network, in the sense that they're stingy about what kind of network resources or how much of network resources they are deploying on those factory floors, because their focus is on the operations part first. And the communication patterns are very different. You don't have a large packet sizes up until now. It is mostly a command-based system. You will have a register in the command and a register where you want to send a 2-byte or a 1-byte command for a machine to move in a specific direction or with a specific pressure applied onto it. But with automation, these things are changing. So with when we start talking about IT-OT convergence, the decision to move IT servers on factory floors will become one of the biggest questions. So right now, your factory floors are very focused on OT related technology, operations technology. And when you start talking about industry protocols, IP, and if you want to take IP all the way down to the devices, it is going to be an overhead. Another scenario which is evolving is virtualization. In this case, right now, so far we have physical PLCs on the factory floors, but with virtualization, they are talking about virtual PLCs. And that brings a question that where would want to place that software? Will that be on the factory floor or on the edge or somewhere in the cloud? And very much related to that is sophisticated compute platform. Do you want to really make your factory floor network complex enough, and you want to bring all those compute intensive servers which run on IT platforms on the factory floor, or would you want to place them somewhere in the edge or cloud, or how would you want to extend them? There are also implications on data growth. And the reason for that is so right now everything was like a push. You want to put a command, you want to send a command down to a specific machine on the factory floor. But now, in order to collect a lot of telemetry, additional sensors are being installed. And those sensors will continuously send the data up to wherever you have some kind of statistics or telemetry control system. And you want to feed that into your business logic to see how your inventory is doing. When do you want to start the process, or when do you want to finish the process? What will be a good time to start a particular manufacturing cycle? So in order to make all those decisions, you need to collect a lot of sensory data, and that will cause the data growth. And the fourth aspect, which normally people generally do not discuss, is that even on the factory floor, there are different kinds of infrastructure interplaying with each other. You could have a building automation system where you want to control air conditioning, cooling, and lighting of the plant. And you could also have some kind of security system, intruder detection, that who's coming in or out of the factory. You would also have additional cameras installed just for the quality control and inspection. All these are different applications, specific networks serving different kind of purposes. And from the automation perspective, to have a single view of your system, you would want to integrate those things together. And we want to study how IETF-based protocols or IT technologies can play a part there. And from a high level, we looked at two key challenges. One is the heterogeneity. We talked about that there are different infrastructures on the same factory floor. And actually, there are around 100 different protocols, field bus related. They are Modbus, Profibus, building automation, and whatnot. And within them, there are different variations based on vendors or some small group of companies standardizing a particular protocol just among themselves. And then there are a lot of, what that means is in order to absorb that heterogeneity, there are multiple stateful gateways are required on the factory floor. You're always translating from one protocol to the other protocol, which is not really an efficient and scalable way, especially when you start adding a lot of sensors and more number of devices. There is also
sorry, you have 1 minute left.
Okay, so automation, I already talked about that. How do you go from device to all the way to the cloud? What are the mechanisms that we need to install in order to make that happen? And when we were looking at these things, obviously addressing came as one of the key differentiator. If you look at the figures on the right-hand side, IP addresses are pretty much fixed in terms of the stack, or the kind of network stack we talk about. Whereas in industry protocols, you have and different kinds of protocols sitting on top, and it's most of the times it is just an application PDU which is riding on the physical interface or the layer 2. And how could we simplify these things? On the left-hand side is the current state of work where you have state in the industry where you have different protocols, stacks. And what we think is that if we had some kind of asymmetric addressing mechanism where your address formats for the source and destination were different, but you could still do a communication between them, that will really simplify your network architecture on a factory floor. And so these are the potential work areas. You could look at it from the device perspective in the industry, on the factory floor, from the network layer perspective, and some additional stuff on the network, that how can you make encapsulation pre-communication between devices and the cloud. So we'll continue to have these discussions in the IoT ops and come up with a very comprehensive document on scenarios and the requirements, and possibly go deeper into the addressing aspects of it. So we just wanted to share this with Intarea Group and see if there is any interest here. And if you would like to have discussions on Intarea Group, I'll definitely bring this work there. And thank you.
Thanks, Kiran. Are there any questions right now for Kiran? All right, seeing none. If anyone has any other comment, please bring it up to the list and provide your feedback there. Moving on, we have Fred.
Right.
Yes, so we're granting you access now to share. We can see it now.
Okay, very good. Yes, my name is Fred Templin. I'm with Boeing. I want to talk about transmission of IP packets over overlay multi-link network interfaces, or OMNI interfaces. So what the transmission of IP packets over OMNI interfaces is about a single non-broadcast multiple access network interface that gets exposed to the IP layer, and it presents a 9 KB MTU to the IP layer. But underneath, it's configured as an overlay over multiple underlying physical or virtual interfaces that may have heterogeneous MTUs. Within the OMNI interface is a service known as the OMNI Adaptation Layer, or the OAL, and it's a minimum mid-layer encapsulation that maps the IP layer to the underlying interfaces. It's very similar to AAL5 from the old ATM days. The work is very closely related to draft Templin 6-man Aero, and Aero and OMNI were formerly discussed in the 6-man working group but not adopted there. And so now we're seeking adoption in the routing working group for Aero and the Intarea working group for OMNI. The work is also very closely related to, but separate from, a draft that was in Intarea called Intarea Tunnels that apparently has been expired for the past several months. So talking about Aero and OMNI in a single internetwork example, we have client nodes that connect to access network subnetworks via one or more data links. Those subnetworks then connect to the internetwork via proxy servers as subnetwork edge nodes, and those proxy servers act as IPv6 routers or IPv6 neighbor discovery proxies. Bridges in the internetwork establish a spanning tree over the internetwork using IPv6 unique local addresses, ULAs. And the OMNI adaptation layer in all nodes that configure OMNI interfaces use IPv6 encapsulation and see this spanning tree as a layer 2 service, the same as if it was a bridge campus LAN. So then we can go from the single internetwork case to look at the bigger picture where we have arbitrarily many internetwork segments joined as NBMA link. Segment routing over the concatenated internetworks using OAL forwarding. Some examples of internetworking segments would include the IPv4 internet, the IPv6 internet, corporate enterprise networks, cellular operator networks, aeronautical telecommunication service provider networks. And one thing to note is that the clients may also connect to multiple distinct segments at the same time. It's not shown in this diagram to reduce complexity, but in the big picture, we can have arbitrarily many segments, internetworking segments, connected together into a single NBMA link using encapsulation at the OAL layer. So what this Omni interface looks like is that the Arrow and Omni clients, proxy servers, and bridges configure Omni interfaces as the node's connection to the Omni link. Client Omni interfaces are configured over multiple underlying interfaces, and they connect end user networks to the Omni link. So if you see the diagram in the upper left, you have the IP layer in the end system configured over an Omni interface. Within the Omni interface, the Omni adaptation layer maps the IP layer to the underlying interfaces that are shown here as L2, IF1, IF2, and IFN, and so forth. The Omni interface uses IPv6 encapsulation to span the entire concatenated internetworking path in a single NBMA layer 3 hop. And all Arrow and Omni nodes are seen as neighbors on the link, as is shown in the right-hand diagram. So the Omni link is an overlay over arbitrarily many internetworks with all nodes on the Omni link that configure Omni interfaces, that is, seen as neighbors on the link. So Omni client underlying interfaces can be coordinated with their proxy services in one of several ways. First, we have direct connect, otherwise known as point-to-point client underlying interfaces, and these connect directly to the proxy server at layer 2 over point-to-point media without traversing any layer 3 hops. Then with VPNs, the client's underlying interface uses network layer security to establish a virtual link to the proxy server over one or more L3 hops at the layer below the VPN, that is. Access network interfaces are in which clients' underlying interfaces connect to a secured access network, such as an enterprise or operator network, that have layer 2 or layer 1 security provisions on the path to the proxy server, which then connects out to the external internetwork. And then finally, internetwork interfaces are clients' underlying interfaces that connect directly to an external internet where the proxy server may be one or more L3 hops away. And the clients may be located behind one or several network address translators in the internetworking case. But the point is that clients may have diverse underlying interface types which connect to multiple distinct internetworks, as opposed to all via the same internetwork. For example, an net interface connect to a public internet, an ANET interface connected to a cellular operator network, a direct interface connected to a dedicated enterprise network proxy server, etc. They're all possible within the same Omni interface to have multiple different distinct types of underlying interface connections. So then what it looks like in terms of the stack is, if you see the stack orientation on the left-hand side, you have the network layer, which is where original IP packets come from, are presented to the Omni interface. Within the Omni interface, we have many different encapsulation sublayer possibilities before the packets are then mapped to the outgoing underlying interfaces. So again, the Omni interface inserts a mid-layer encapsulation between layer 3 and the underlying interfaces using minimal encapsulation with effective header compression. Mid-layer segment routing is used as necessary to traverse spanning trees over disjoint internetworking segments, and then route optimization is used to avoid strict spanning tree paths. So in terms of Arrow and Omni addressing, some of the earlier talks were talking about variable length addressing. We're looking strictly here at the standard IPv6 and IPv4 addressing architectures, not assuming any kind of variable length addressing. So we would say that each client would have an IP global unicast address prefix, whether it would be IPv4 or IPv6. That's also known as a mobile network prefix. And that gets advertised to downstream attached end user networks where we might have Internet of Things devices, for example. So an example prefix would be 2001 DB812:/64. And again, end user network applications use mobile network prefix addresses as the source and destination addresses of original IP packets. Each Arrow Omni node configures an IPv6 link local address. That's for use in IPv6 neighbor discovery messaging. Clients configure mobile network prefix link local addresses. So for example, for the delegated prefix 2001 DB812:/64, the mobile network prefix link local address is
FE80 link local, followed by the interface identifier 2001 DB812. That's what's known as the arrow address construction from that mobile network prefix. Now, meanwhile, proxy servers and bridges, which are fixed infrastructure elements, configure administrative link local addresses with the least significant 32 bits set according to the segment routing topology node number in your subnetworking. So, for example, if the segment routing topology subnet was 2001:1000, then the administrative link local addresses within that subnet are assigned as FE80::2001, 1001, 1002, 1003, and so forth. They're administratively assigned addresses assigned to fixed infrastructure elements. Now, each Arrow and Omni node also configures an IPv6 unique local address, which is formed by simply taking the ULA prefix for the Omni link. For example, FD00:01, 02, 03, 04, 05, and taking the interface identifier suffix from the link local address and putting that into the interface identifier of the unique local addresses. You can see in this LAN address here below. Clients, proxy servers, and bridges use ULAs as the OAL header, source, and destination addresses when IPv6 encapsulation is used by the OAL. I think I'll skip this part talking about any cast addresses because it's not really relevant to the Omni discussion. And also the Arrow and Omni routing system, what's being shown here is the spanning tree I referred to earlier in the green segments that span the interconnected internetworking segments. There's a secured spanning tree in which the spanning tree is configured over IPsec, WireGuard, etc. at layer 2, and the unsecured spanning tree which travels over the same hop, but there are no L2 security provisions provided. Control messages always travel over the secured spanning tree. Data messages travel over the unsecured spanning tree, so that any kind of routing that gets established is through secured neighbor discovery messages that are carried over the secured spanning tree. Now, really where I want to focus in on this talk for today's session with the Intarea is what this Omni interface does and what the Omni adaptation layer does. So we have an original source that sends an original IP packet that travels through some edge internetwork until it reaches a node that attaches to the Omni link, which is shown in this lavender colored cylinder. And that node is known as the OAL source. The OAL source has an Omni interface as shown in this stack diagram here. And it performs what's known as OAL encapsulation, which inserts an IPv6 encapsulation header and a trailer checksum. After the encapsulations are included, the OAL then fragments the packet if necessary to create carrier packets that are guaranteed small enough to traverse all paths. So the Omni interface has a 9180 by MTU. Within the Omni interface, the OAL fragments the packet if necessary to make sure that all of the carrier packet fragments will traverse any concatenated paths, networks in the path without loss due to size restriction. So what we know is that for IPv4, the maximum receive unit is 576 bytes. So what that says is without any further knowledge, we can always assume that carrier packets less than 576 bytes will travel any internetworking paths without loss due to a size restriction. So that's what we know without any advanced information. But if we know that the path can carry larger, then we can fragment to a larger size, for example, 1500 bytes. So the original source then can tune the packet sizes to achieve optimal performance based on hard or soft MTU feedback that comes back from the network without loss. And this provides for a lossless path MTU discovery service between the OAL source and the OAL destination. And then the original packet is finally delivered to the final destination on the edge networks that are beyond the OAL destination. So what happens when we have concatenated internetworks is that we have the OAL source and OAL destination are joined through OAL intermediate nodes that traverse those intermediate internetworking regions.
So again, the OAL source and final destination are in different internetwork segments. The OAL source produces carrier packets, and the OAL destination reassembles them. And the OAL intermediate nodes, which are also known as bridges, join the network segments in a spanning tree. And we have support for global mobility and route optimization with dynamic MTU tuning. And again, this is a lossless path MTU discovery with an assured MTU of 9180 bytes. Now, we use on the Omni interface IPv6 neighbor discovery messaging for neighbor coordination and for establishing layer 2 routing information across the concatenated internetworks. The IPv6 neighbor discovery messages include an Omni option. And the purpose of the Omni option is to assert protocol conformance, to synchronize windows between Omni peers, and to exchange configuration information. So on the right, you see what this Omni option looks like. This is a new IPv6 neighbor discovery option type. The type field has the new type that we'll be getting from IANA. The length is obviously from TLV format. And then we have information including the sequence number, acknowledgement number, and window size for synchronizing identification sequence numbers between the Omni source and the OAL destination. And then the sub options contain the configuration information to be passed. So the Omni options sub options include fields that determine the protocol operations. There are multi-link forwarding parameters, interface attributes, traffic selectors that determine addresses and other parameters for specific underlying interfaces. We have DHCP, HIP, PIM sparse mode messages that combine the functions with the IPv6 neighbor discovery as a wrapper. And then we have reassembly limit fragmentation, report ICMP error, etc., to provide Omni destination feedback to the source. So these are the sub options that can occur within the Omni option. Now, when a client comes onto the network and locates proxy servers, it performs router solicitation advertisement messages either directly to the proxy server or using the proxy server as a proxy middle box. So when a client sends an RS message to a proxy server A with all routers multicast or the administrative link local address of A as the destination, A assumes the router role and returns an immediate unicast RA while injecting the client's mobile network prefix into the routing system. When a client sends an RS message to proxy server B with the administrative link local address of A as the destination, but B instead assumes the proxy role and forwards the RS message to A, which returns a unicast RA to client B via client B as a proxy. So then proxy server A becomes the hub, also known as the default router or mobility anchor point in a hub and spokes arrangement with all other proxy servers B star as the spokes. And the client can later switch to a different hub by sending new RS messages. So what that looks like in terms of the figure, here we have the client has sent a first RS message to the proxy server that you see shown in green. And that becomes the default router or the hub proxy server. Other proxy servers for the other underlying interfaces of that client are shown in red are treated as proxies, and they forward the RA messages between the proxy server and the client as spokes in a hub and spokes arrangement. So now, in terms of the MTU hard and soft errors I was referring to, RFCs 1191 and 8201 provide ICMP packet too big error messages that always report packet loss due to a size restriction or a hard error. Whenever one of these packet too big messages comes back, it's always because a packet was dropped because of a size restriction. But what Omni is asking for is a new packet too big code to indicate a soft error. In this case, the packet is still delivered, but the error informs the source that it should reduce the size of the packets that it sends in future packets, because for some reason, the network has experienced a level of discomfort for passing packets larger than this size. So with these packet too big soft errors, sources can dynamically tune the sizes of the packets they send to get the best performance without loss-related retransmissions on a per-flow basis. It could be that some flows will have a better packet size of, say, 4K bytes. Other flows might prefer a packet size of 1,500 bytes. Still others might prefer a packet size of 9180 bytes. And they can all be dynamically tuned through soft errors instead of packet to big hard errors. When the source and target client's underlying interfaces connect via an open internet, where there's a very good chance they may be located behind one or more network address translators. Each client naturally establishes NAT mappings when it performs an RS-RA exchange with its first hop proxy server, but these mappings are generally not viable for client exchanges with other Arrow Omni nodes besides that first hop proxy server. So that when an Arrow Omni route optimization is applied, route optimization peers must perform neighbor solicitation, neighbor advertisement messages, and bubble exchanges to establish NAT mappings for itself in the NATs on the path to the target client. And these NAT traversal procedures are conducted in the same manner as for RFCs 4380 and 6081. So then for signaling other things that are going on in the Omni link, IPv6 neighbor discovery message, unsolicited neighbor advertisement messages are used. Hub proxy servers announce client state changes such as mobility related address changes, link quality changes, traffic selector changes, and other factors by sending unsolicited neighbor advertisement messages to all nodes that has recently sent a neighbor advertisement for address resolution message to. So when the nodes that receive these unsolicited neighbor advertisements, they can update their state information for the client, which may require new NSNA NUD path state exchanges. New hub proxy servers send UNAs to inform an old proxy server that the client has departed and chosen a new hub proxy server. And when the old hub proxy server receives that message, it records the new hub proxy server address, withdraws the mobile network prefix route, and forwards unsolicited neighbor advertisements to nodes that has recently sent a neighbor advertisement to. And then finally, target nodes request selective link layer retransmissions by sending unsolicited neighbor advertisements to the source with identifications and orderal numbers of any missing fragments. When the source node receives these UNAs, it retransmits the requested fragments if it still has them in its retransmission cache. And the retransmission window should be brief, and that determines the link persistence. It's not true end-to-end reliability. It's opportunistic and best effort link persistence and link retransmissions. So finally, here we have a pointer to the draft, and we're wondering if this is something that could potentially be adopted as an IETF Intarea working group item. And I'll stop there since I'm out of time for any questions that there might be.
Thanks, Brad. Indeed, we are at the end of the hour, but we might drag for a couple of minutes if people have any questions right now. Otherwise, please bring it to the list. But we can take a couple of questions if people want to hear. Okay, seems like it's getting late for people right now, but thanks a lot, detailed presentation. And indeed, I think if you're looking to get and ask for adoption, we should get a little more support from the group. So please bring the discussion to the list so that we can judge if this is something that the group would like to adopt.
Yep.
All right. So thanks everyone, the presenters, Wasim, Eric, for attending.
Thank you.
Hopefully you had a fruitful and interesting meeting, and we look forward to seeing you virtually or physically at the next meeting. Thank you very much.
Thanks, everyone.
Good night.